This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a fascinating paper exploring the visual capabilities of state-of-the-art visual language models, VLMs. The authors systematically assessed 3 leading VLMs using a comprehensive battery of neuropsychological and experimental visual tests, comparing their performance to that of healthy human adults. What are your initial thoughts on this approach to evaluating VLM visual abilities?
It's a highly rigorous and insightful approach. Using established neuropsychological tests provides a standardized and clinically relevant framework for evaluating visual function. This contrasts with many VLM evaluations that focus solely on benchmark datasets, which may not fully capture the nuances of human visual perception. The inclusion of experimental psychology tests further strengthens the methodology, allowing for a more granular analysis of specific visual processes.
The paper highlights a surprising paradox. VLMs excel at complex visual reasoning tasks but struggle with seemingly simpler, low-level visual abilities. Can you elaborate on this finding and its implications?
This mirrors Moravec's paradox, where tasks that seem easy to humans, like perceiving orientation or resolving occlusion, are surprisingly difficult for AI. The VLM's success in high-level tasks, such as object recognition, likely stems from their extensive training on large image text datasets. However, these datasets may not adequately represent the foundational visual concepts crucial for low-level processing. This suggests that complex object recognition can be achieved without necessarily developing a robust understanding of fundamental visual features.
The study used a diverse range of tests categorized into low, mid, and high-level visual processing stages. What were the key differences in VLM performance across these stages?
The VLMs significantly underperformed humans in low and mid-level visual tasks, which involve processing basic visual features like orientation and size, and perceptual organization like figure ground segregation. In contrast, they performed comparably or even better than humans on high-level tasks, such as object recognition, which rely on semantic knowledge and contextual understanding. This suggests a hierarchical deficit, where the lack of foundational visual skills hinders performance on more complex tasks requiring those skills.
The paper mentions that all 3 VLMs exhibited similar strengths and weaknesses. What does this suggest about the underlying limitations of current VLM architectures?
The high correlation in performance across the 3 VLMs, despite their architectural differences, points to a common underlying limitation. This suggests that the current approach to training VLMs, primarily relying on large image text datasets, may not be sufficient to develop comprehensive visual capabilities. The models might be effectively memorizing patterns rather than truly understanding the underlying visual principles.
The authors discuss several potential explanations for the VLM's deficits, including limitations in the training data and the binding problem. Can you expand on these?
The training data may lack sufficient representation of low-level visual features and their relationships. The binding problem refers to the difficulty of integrating multiple visual features to form a coherent representation of an object. VLMs may struggle with this, leading to difficulties in tasks requiring the integration of multiple visual cues. Furthermore, the reliance on textual descriptions and training data might not fully capture the implicit visual knowledge humans acquire through experience.
The paper concludes by suggesting potential avenues for improving VLM visual abilities. What are some of these, and what are their potential limitations?
The authors propose several strategies, including using specialized training datasets focused on low-level visual properties, fine-tuning the text decoders to better interpret visual representations, and employing alternative visual encoders. However, these approaches often require significant engineering effort and may not necessarily lead to human-like visual understanding. The fundamental challenge remains in developing models that can acquire and integrate foundational visual concepts in a manner similar to humans.
The study's use of established neuropsychological tests offers a valuable framework for future research. What other types of tests could be used to further probe VLM visual capabilities?
Future research could explore tests of visual acuity, visual field sensitivity, color perception, and the perception of visual illusions. These tests could provide a more comprehensive understanding of the strengths and weaknesses of VLMs across different aspects of visual processing. Furthermore, incorporating more ecologically valid tasks, mimicking real-world visual scenarios, would enhance the generalizability of the findings.
The paper highlights the importance of considering the limitations of current VLM architectures and the need for innovative approaches to training and evaluation. What are your overall takeaways from this research?
This research provides a crucial benchmark for evaluating VLM visual capabilities, highlighting a significant gap between current models and human visual perception. The findings underscore the need for a more holistic approach to VLM development, focusing not only on high-level performance, but also on the acquisition of foundational visual concepts. This requires careful consideration of training data, model architectures, and evaluation methodologies. The use of neuropsychological tests offers a powerful tool for bridging the gap between artificial and human vision.
The authors also discuss the limitations of their study, such as the non-orthogonality of task types and visual stages. How might these limitations be addressed in future work?
Future studies could design experiments with a more balanced distribution of task types across visual stages, allowing for a more controlled comparison of VLM performance. They could also increase the number of trials per test to improve the precision of performance estimates. Furthermore, exploring the use of open source models would allow for greater transparency and insight into the model's internal mechanisms.
The study focuses on closed source models. What are the advantages of using open source models in future research?
Open source models offer greater transparency, allowing researchers to examine the model's internal representations and understand their decision-making processes. This would facilitate a deeper understanding of the underlying reasons for VLM's visual deficits and inform the development of more effective training strategies. Techniques like saliency maps could be used to visualize the model's attention patterns during task performance.
The paper suggests that the observed visual deficits might not be easily addressed through incremental updates to existing VLMs. What fundamental changes might be needed?
Fundamental changes might involve rethinking the training data and incorporating more detailed textual descriptions of low-level visual features. This could involve creating datasets specifically designed to teach VLMs about fundamental visual concepts, rather than relying solely on existing image-text pairings from the web. Furthermore, exploring alternative architectures that better capture the hierarchical nature of human visual processing could be beneficial.
The study's findings have implications for the broader field of artificial intelligence. How might these findings influence the development of more general-purpose AI systems?
The findings highlight the importance of developing AI systems with a more comprehensive understanding of the world, including foundational perceptual abilities. General-purpose AI systems should not only excel at complex tasks, but also possess robust and reliable low-level perceptual skills. This requires a shift in focus from solely optimizing performance on benchmark datasets to developing models that exhibit human-like perceptual capabilities.
The paper's systematic approach to evaluating VLM visual abilities provides a valuable contribution to the field. What are the broad implications of this work for understanding the relationship between human and artificial intelligence?
This work contributes to a deeper understanding of the differences and similarities between human and artificial intelligence, particularly in the domain of visual perception. By using a clinically relevant framework, the study provides insights into the limitations of current AI approaches and highlights the need for more sophisticated models that can truly mimic human-like perception. This has implications for various applications of AI, from robotics and autonomous driving to medical image analysis and assistive technologies.
The study's findings challenge the assumption that complex visual reasoning automatically implies competence in low-level visual tasks. What are the implications for future research on AI and cognitive science?
The findings suggest that future research should focus on developing AI systems that possess a more comprehensive understanding of the world, including foundational perceptual abilities. This requires a closer collaboration between AI researchers and cognitive scientists to better understand the principles of human perception and cognition. This interdisciplinary approach is crucial for developing AI systems that are not only powerful, but also robust, reliable, and aligned with human values.
The paper mentions the potential for using chain of thought, COT, visual language models to gain further insights into VLM reasoning processes. How might this approach contribute to a better understanding of VLM limitations?
Analyzing the chain of thought used by COT models during visual reasoning tasks could reveal the specific steps and reasoning processes that lead to errors. This could pinpoint the exact points of failure in the model's visual understanding, providing valuable insights for improving their performance. By examining the intermediate steps in the reasoning process, researchers can identify specific areas where the models struggle and develop targeted strategies for improvement.
The study's findings suggest that simply increasing the amount of training data might not be sufficient to address the observed visual deficits. What other factors might be crucial for improving VLM performance?
Beyond the quantity of data, the quality and diversity of the training data are crucial. The data should include a balanced representation of low-level visual features and their relationships, as well as diverse visual contexts and scenarios. Furthermore, the design of the model architecture itself plays a significant role. Architectures that better mimic the hierarchical nature of human visual processing might be more effective in acquiring foundational visual concepts.
The paper highlights the importance of using validated neuropsychological tests to evaluate VLM performance. What are the advantages of this approach compared to using only benchmark datasets?
Neuropsychological tests provide a standardized and clinically relevant framework for assessing visual function, offering a more comprehensive and nuanced evaluation than benchmark datasets. These tests are designed to assess specific aspects of visual processing, allowing for a more granular analysis of VLM strengths and weaknesses. Furthermore, the availability of normative data from human populations allows for direct comparisons between VLM and human performance.
The study's findings have implications for the development of AI systems for various applications. Can you provide some specific examples?
The findings are relevant to applications such as autonomous driving, robotics, and medical image analysis. For example, robust, low-level visual processing is crucial for autonomous vehicles to accurately perceive their surroundings and avoid accidents. Similarly, reliable visual perception is essential for robots to interact effectively with their environment. In medical image analysis, accurate interpretation of medical images requires a deep understanding of visual features and their relationships.
The paper emphasizes the need for interdisciplinary collaboration between AI researchers and cognitive scientists. How can this collaboration contribute to advancing the field?
Interdisciplinary collaboration is crucial for bridging the gap between artificial and human intelligence. Cognitive scientists can provide valuable insights into the principles of human perception and cognition, informing the design of more human-like AI systems. AI researchers can leverage these insights to develop more sophisticated models and evaluation methodologies. This collaborative approach is essential for developing AI systems that are not only powerful but also robust, reliable, and aligned with human values.
In conclusion, this paper offers a valuable contribution to the field by providing a rigorous and systematic evaluation of VLM visual capabilities. Thank you for this insightful discussion.